Hello students. So this is our second lecture on phase equilibria. In the first lecture we have discussed basic concepts of phase equilibria and one component systems. In this lecture we will be discussing mainly about two component systems. The two component system means that the number of components present in the system will be 2. The value of C will be equal to 2. So if we put up the value of components in the Gibbs space rule equation, then the degree of freedom for such a system by substituting the value of C in equal to 2 comes out to be 4 minus P. So depending upon the value of P, we can have the value of degree of freedom for this system. For example, if the value of P is 1, that means if there is only one phase, number of phases is 1, by substituting the value over here as 1, 4 minus 1 means 3. That means degree of freedom of the system at a point where there is only one phase will be 3. That means that system will be a trivariant system, and if we are to define that system, then three variables they are to be defined, that is temperature, pressure and concentration. So we require the value for all the three of these variables in order to define completely this type of system where the number of phases are 1 and degree of freedom is 3. Similarly, if in a two component system we are having number of phases equal to 2, then substituting the value of P as 2, that means degree of freedom will be 4 minus 2, it will be equal to 2. So that means such a system will be a bivariant system, and we have to specify only two variables to completely define such a system. And those two variables, they may be temperature and pressure at a constant concentration. Similarly, if we are having three number of phases, by substituting the value of P as 3, the degree of freedom comes out to be 1. That means such a system will be a monovariant system. And in monovariant system, that means one variable is to be specified. So that variable can either be temperature or it can be pressure. And if the number of phases are 4, 4 minus 4 means degree of freedom will be 0. That means at such a point where in two component system the number of phases are 4, the system will be invariant. So invariant system, then at that point that means there will be a definite value of temperature and pressure, and such a point will be called as triple point or quadruple point or eutectic point, depending upon what kind of two component system we are using. Then in case of two component systems, if C is 2, P is 1, as you have seen that F is equal to 3. And if degree of freedom is 3, that means we need three-dimensional figures which are not conveniently represented on paper. So in generally what is done in such systems is that they are represented by any two of the three variables and keeping the third as constant. So in such cases then these three combinations, they are possible for representation of such a system. The pressure temperature phase diagram means that two variables, they will be pressure and temperature, and here the concentration will be kept as constant. Then second category can be temperature and composition, and here the pressure will be kept constant. And then third category is composition and pressure, where temperature can be kept constant. So we can use any of these three combinations to represent such systems in a two-dimensional figure in the on the paper. So out of these three combinations, the most convenient ones, they are temperature composition diagrams, because these are the two variables which are most convenient to be taken into consideration for two component systems, and pressure is kept constant in such cases, because in the phase diagram there is not much change in the temperature over a variation of either temperature or concentration. And these are the different types of equilibria which are present in two component systems. That can be a liquid vapor equilibria, solid liquid equilibria, solid vapor equilibria, or liquid to liquid or solid to solid equilibria. This liquid to liquid means the liquid phase of one component in equilibrium with liquid phase of the other component. Solid phase of one component in equilibrium with solid phase of the other component. So these are the various equilibrias which are present in two component system. Now, out of these solid liquid equilibria, uh, solid liquid equilibria is the most important equilibria to study for two component systems, and here we will generally ignore the vapor phase. Vapor phase is ignored because we are to draw the diagram at constant pressure, and in such cases there is no major change in the pressure over a phase diagram of solid liquid system. So under such circumstances, these types of systems, they are called as condensed systems, and they are usually studied at constant pressure, and pressure is kept constant to the value of 1 atmospheric pressure. So when pressure has been kept constant, that means we have to modify the Gibbs phase rule equation then. Because in the Gibbs phase rule equation which you have used, we have used is that F is equal to C minus P plus 2. This is the Gibbs equation. But once we have kept the pressure constant, that means degree of freedom is to be reduced by 1. So 2 minus 1 comes out to be 1. So the reduced phase rule equation becomes F is equal to C minus P plus 1. So for these two component systems, we will be using this reduced phase rule equation for all the cases for solid liquid system. And in these types of system, that means by substituting these values, components C is 2 for two component systems, and this 2 has been reduced to 1. So 2 minus p plus 1 means 3 minus p. So this is how we will be calculating the degree of freedom in such type of solid liquid equilibrium. So degree of freedom will be 3 minus p. And solid liquid equilibrium is of three types. One is where two components, that is solid and liquid components, they are completely miscible. That solid is miscible with the liquid. Then second category is they are partially miscible, and third category is they are not miscible. That means they are immiscible. So completely miscible, completely immiscible, and partially miscible. So these are the three category of systems. In case of solid liquid equilibria, they need to be studied. So first two component system which we will be studying is lead silver system. Lead silver system is a two component system, as the composition of each phase can be represented with the help of two species, and these two species, they are lead and silver. So at point A we are having pure lead, melting point is 327. At point B we will be having pure silver, melting point is 961. So, and over this phase diagram, from any or from this point to this or this point to this, we will have all types of liquid solid mixtures. So in this area we will be having solid lead plus liquid. In this area we will be having the liquid state of lead silver mixture, all liquid states, which is called as liquidus. Then in this area we will be having solid silver plus liquid, and in this area solid silver plus eutectic mixture, solid lead plus eutectic mixture. Eutectic mixture is that when the two compounds they do not react chemically to form compound, they are simply a mixture which is homogeneous in nature. So such a mixture is called as eutectic mixture. That is, both molten lead and silver, they are in the molten state and they are miscible in all proportions to give us a homogeneous mixture. Such a homogeneous mixture will be called as eutectic mixture, and such a system we will call it as a eutectic two component system. And in this type of eutectic two component system, these are the four phases which will be present in the phase diagram. One is, at some point we will having solid lead, solid silver, solution of lead and silver, and then the vapor phase. Now, as you have seen that boiling points of silver and lead, they are very high. The gaseous phase is practically absent in the system. So that is why we will be using only reduced Gibbs phase equation, that is F is equal to C minus P plus 1. And because the pressure has negligible effect on the equilibrium in the solid state or in the molten state, so here when F is equal to 0, then number of phases which can be present maximum is 3, not 4, because now we are using reduced Gibbs phase solution. Now there are mainly two curves in the phase diagram. These are called as phase curves. First is AE curve and then is BE curve. The AE curve shows the effect of addition of silver on melting point of pure lead. So as you have seen that at point A, that is at 327 degrees centigrade, this is melting point of pure lead. So as we move from A to A, the pure lead will be mixed with the liquid lead and vapor as we move from here to here, and then the silver solution will also be in equilibrium. And this curve is called as melting point or freezing point curve of lead. So as we move from here to here, the temperature decreases, and the lead from 327 to 303, we reach at point E, which is a eutectic point. Then curve BE This shows the effect of addition of lead on the melting point of pure sulfur. So this is the 961 is the melting point of pure silver. As we move from here to here, then along this curve we see what will be the effect of addition of lead on the melting point of silver. So melting point of the silver goes on decreasing as we move from here to here when we add lead to it. So this is called as melting point curve or freezing point curve of silver. As I've told you that melting point of pure silver is 961, whereas pure solid silver, liquid silver and vapor, they coexist at this point. And melting point of silver falls gradually along B with addition of lead. As I told you that this goes on decreasing. And at point E, which is called as eutectic point, both the curves AE and BE, they meet at this point, and the three phases which are in equilibrium at this point, they are solid lead, solid silver and their liquid solution. And at this point the degree of freedom will be 0 because there are three phases which are present at this point. And at this point temperature is 303 degrees centigrade, and this is the composition of silver and lead which is there at point E. 2.6% of silver is present and 97.4% of lead is present at E. So as we move from E to the right, either this way, the composition of silver will increase and composition of lead will decrease. You can see here at this point the composition of silver is 2.6%, but as we move towards this, at this point the composition of silver will be 100% and lead will be 0%. Similarly, if we move from here towards this end, that is left side, then concentration of lead goes on increasing and concentration of silver goes on decreasing. So you can see over here the silver is decreased from 2.6 to 0%, whereas this increases from 97.4% to 100%. So by changing the conditions uh, either towards right or towards or towards left, we can change the concentration of the eutectic mixture. So either we can have 100% pure silver or 100% pure lead at these points. Then a very important application of lead silver system is in the desilverization of lead, and this process is called as Pattinson process. So what is done here is that in the process we are having argentiferous lead which contains very small percentage of lead that is first heated to temperature well above its melting point. So the system contains only the liquid phase, which in the liquid phase we will be having both lead and silver. And percentage of silver present in this mixture is say 0.1%. And at point M in the phase diagram, which is above the phase curve AE. So here both the phases they will be in the liquid phase. So as we move down from M to N, the system is allowed to cool gradually, and as it is allowed to cool gradually without any change in concentration, so that means only temperature is varied, the temperature is reduced from high temperature to low temperature. And when at a constant concentration point N is reached, the lead will begin to crystallize out from the solution. And this will increase the amount of silver present in that solution. So this is how we can separate silver from a mixture of argentiferous lead. So you can see over here, this was the point M where both lead and silver, they are present in the liquid form. And as we move from M to N, that is at constant concentration, temperature is reduced. So at this point, the lead will start separating out from this mixture. And when lead will start separating out, that means the concentration of lead will decrease in the mixture and concentration of silver in the solution will increase. So here that means you in this area, as you know, solid lead plus liquid is there. So as we move from N to O, at O, then which is the temperature equivalent to E, we will have a more concentrated form of silver. The percentage of silver will increase at this point as we cool this at a constant concentration. So similarly, if we move on at this point, say movement of the temperature is from here to here, so at point E we can see that the percentage of silver can be 2.6%. So we have started with the material which was having 0.1% of silver, and while we are cooling at constant concentration, the percentage of silver has increased to 2.6% by separation of the solid lead. And this process of increasing the percentage of silver in the alloy is known as Pattinson process. So practically this is done through these ladles. These are known as ladles where we are cooling the mixture at a constant concentration. So you can see over here in the first instance we are having a mixture of argentiferous lead. So as we cool along the line MnO, at point N, the lead starts coming out in the form of solid, which can be separated out. That means the concentration of silver in this solution will be increasing as the solid lead separates out. In the second ladle, then more of lead separates out and the concentration of silver again increases more till it reaches at point E, where the concentration of the silver can be 2.6% and lead can be removed up to 96.4%. So this process is known as Pattinson process. Then second system is potassium iodide water system. This is again an example of two component system which involves salt and water, and the potassium iodide is present only in anhydrous forms. No hydrated forms are present, so we will have these four phases which are present in this two component system. One is solid potassium iodide, ice, solution, and vapor phase. And the phase diagram, as you can see, is similar to what we have seen in case of lead silver system. But the only difference is that the two systems is that melting point of potassium iodide is very high, even higher than the critical temperature of water. So therefore it is not represented in the phase diagram. So melting point of salt is not represented in the phase diagram. So that is why this is not extrapolated to the other end of the phase diagram. Now here in Ki water system, the two curves, that is curve AE and curve BE. The curve AE and curve BE, uh, that is freezing point curve of water is curve AE and solubility curve of Ki in water is curve BE. So here you can see the freezing point curve of water, the temperature is 0 degree centigrade. So point A, this is melting point of ice or freezing point of water. Temperature we know here is 0 degree centigrade and pressure is kept constant, that is 1 atmospheric pressure. Here the equilibrium exists between ice, water and vapor. So as we move from A to E, there is a solution of potassium iodide present in this area, and in this area we will have solid ice plus solution means potassium iodide solution. Then in this area we will be having solid potassium iodide plus solution, that is Ki dissolved in water is known as solution. Then E is the eutectic point, and at eutectic point the percentage composition is 52% of potassium iodide is present and 48% of ice is present. And at eutectic point E, the temperature is minus 23 degree centigrade. So all along at different points we can have different type of equilibria. So for example, when we move from M to N, at M, point M, we will be having a solution of potassium iodide. So potassium iodide dissolved in water. So as soon as we reach point N, that means here along with the solution we will be having solid ice also. Then similarly at this point from X to E, again we are having solution, and here the three phases they will be in equilibrium, that is solid ice and potassium iodide and solution. The fourth one is vapor, which is ignored. So as I've told you that curve BE, this gives us the effect of increasing of temperature on solubility of potassium iodide in water, and solubility of Ki increases with increase in temperature and is highest at point B. So if we move from point B to E, that means solubility decreases. If we move from E to B, the solubility goes on increasing as we move from E to B with the rising temperature. And as I have told you that BE cannot be carried to 100% access because we don't extrapolate it up to the boiling point of the potassium iodide. The melting point of the potassium iodide is very high. And here because temperature and concentration both are fixed at point B, so here the system will be invariant. The degree of freedom will be 0. Whereas along the curve BE, the degree of freedom will be 1. Then point E, which is also called as cryohydric point, the point E is where both the curves AE and BE they meet. This is called as cryohydric point. And here the phases in equilibrium are solid potassium iodide, ice and solution phase. And if we have neglected the vapor phase, if vapor phase is not neglected, that means there are 4 phases in equilibrium at point E. So that is why this is also known as quadruple point. In addition to its name as cryohydric point, this is also called as quadruple point because the fourth phase we have neglected, that is the vapor phase. But in actual, that phase is present. So, as per the reduced Gibbs phase rule equation at constant pressure, the system will be non-variant or invariant as the degree of freedom will be 0. So, eutectic point in case of salt water systems is generally known as cryohydric point because eutectic point we were using for the phase diagram where eutectic mixture of two solids was there. Here the salt is soluble in water, so that is why here we call it as the cryohydric point. And at this temperature, as I have already told you, that because this is a quadruple point or cryohydric point, the temperature and composition will be fixed at this point. So temperature here it is minus 23 degrees centigrade and composition is 52% potassium iodide and 48% ice. Then third system is sodium sulfate water system. Again, this is a two component system and two components, they are sodium sulfate and water. But sodium sulfate it exists as two hydrated forms and two crystalline anhydrous forms. So that means there are in all there are 7 equilibria and two hydrated forms are decahydrate and heptahydrate sodium sulfate, whereas anhydrous salts which are existing in two crystalline forms, the crystalline forms of sodium sulfate, they are rhombic and monoclinic anhydrous sodium sulfates. So on the basis of these differentiations, there are these 7 equilibria which are possible, or these 7 phases which are possible in different equilibria. The phases they are solid sodium sulfate decahydrate, solid sodium sulfate heptahydrate, solid sodium sulfate rhombic, solid sodium sulfate monoclinic, then the phases of water, that is ice, then solution of sodium sulfate in water, and then water vapor. So these are the 7 phases which are possible for sodium sulfate water system. So the phase diagram, this consists of 7 curves. That these curves, they are this curve AB, then the curve BC. BC has been shown as a dotted line. Dotted line in the phase diagram means this is a metastable curve. Then curve BF, this is a solid line, that means this is a regular phase curve. Then the curve CD, again a metastable curve. Then curve FD, this is a metastable curve. Then curve FG, then GH, then HI. So these are the 7 different phase curves which are present in the phase diagram. And there is one triple point, that is A. Then there are 5 quadruple points B, then D, F, G, H, not H, G. So these are the different quadruple points which are present in the phase diagram. Then we will discuss these curves and points one by one. First is curve AB and point B. So this is curve AB and here it is point B. So at point A, the temperature is 0 degree centigrade, and this is composition is, it will be having 100% water and 0% sodium sulfate. So that means at 0% we know here the phase will be ice in equilibrium with water. So A is a triple point in which ice is in equilibrium with water and its vapor at 0 degree centigrade. And as we move from A to B, that means as we lower the temperature, the concentration of sodium sulfate goes on increasing, and concentration of water will goes on decreasing. So along the line, that means this is called as freezing point curve of water. The addition of anhydrous sodium sulfate takes place as we move from A to B, and temperature is reduced from 0 to minus 1.3. And three phases in equilibrium at this curve from A to B, they are ice solution and vapor. Ice means solid ice, solution means solution of anhydrous sodium sulfate in water, and the water vapors, they are present in equilibrium with the other two phases. And along the curve, the system is monovariant because there are three phases, and there are two components. The value f comes out to be 1. Whereas at point B, that is minus 1.3 degree centigrade, minus is to be added over here, it is minus 1.3 degree centigrade. At this point, a fourth phase, that is sodium sulfate decahydrate, also appears. And if fourth phase comes at point B, that means here the degree of freedom will become 0 from 1, because number of phase has increased from 3 to 4, the degree of freedom will become 0. The system will become invariant at point B. So that is why B is a quadruple bond. Then the from point B to point C, this curve shown by dotted line is a metastable curve, and point C is a metastable quadruple. And the four phases in equilibrium at point C, they are sodium sulfate heptahydrate, ice solution, and vapor. And the temperature corresponding to this point is minus 3.55 at point C, minus 3.55, and at this point we can have the four phases, and the phase which we have added here is sodium sulfate heptahydrate. And this is a metastable point, quadruple point, because we can reach B to C but not from C to B. That is the cooling from minus 1.3 to minus 3.55, this point can be reached, but we cannot heat from minus 3.55 to minus 1.3 to achieve point B. So that is why the point C is a metastable point. Then is curve CD and point D. So this CD in the dotted line is again metastable solubility curve of sodium sulfate heptahydrate, and here three phases in equilibrium, they are sodium sulfate heptahydrate, solution, and vapor. They are present along this curve, and again because three are present, three phases, the system will be monovariant, degree of freedom will be 1. But as the point D reaches, which is a second metastable quadruple point, then here the heptahydrate will change into anhydrous sodium sulfate. So anhydrous sodium sulfate will make its appearance at this point. And then the curve BF, this curve is BF, and here the equilibrium, at equilibrium we will be having sodium sulfate decahydrate solution and vapor phase, they will be coexisting. And at this point F, which is another quadruple point, the temperature is 32.4 degrees centigrade. And here the anhydrous, the fourth point at point F, the fourth phase which appears is anhydrous sodium sulfate as one of the solid phases. So uh, the form of anhydrous sodium sulfate which comes into play at this point is the rhombic. So that means the four phases at point F which are present, they are sodium sulfate decahydrate, anhydrous sodium sulfate in the form of crystalline rhombic form, then solution of sodium sulfate in water and vapor. These four phases, they are in equilibrium, and at point F, therefore this is a quadruple point, but degree of freedom will be 0. And this point is also called as transition point, because here the 10 water molecules attached to sodium sulfate, uh, they are removed to give us anhydrous sodium sulfate, and these water molecules they go to the solution. That means the concentration of the system along this line changes as the sodium sulfate decahydrate changes into solid anhydrous sodium sulfate. So this water molecules which are lost, they are taken up by the solution. Therefore, at this point, the composition of the solid phase as well as liquid phase becomes different at this point. So that is why, because of this variation in the composition of solid phase and liquid phase, this point is called as transition point. And because of this change, this is also said to represent incoherent melting of sodium sulfate. Incoherent melting point of sodium sulfate. Then is curve FG and point G. So this is curve FG, and point G is again a quadruple point, and this is you have seen that at point F we are having rhombic anhydrous sodium sulfate. So this is a solubility curve of rhombic anhydrous sodium sulfate. And as we move from F to G up to temperature 125 degrees centigrade, the solubility of rhombic sodium sulfate decreases, then it goes on increasing up to point G, that is at 254 degrees centigrade. And here at 254 degrees centigrade at point G, pressure is 27.5 atmospheric pressure. So here at this point, point Z, the rhombic sodium sulfate changes into monoclinic sodium sulfate. So this is again a transition point, because rhombic sodium sulfate changes into monoclinic sodium sulfate. So this is stable quadruple point, and four phases in equilibrium. Therefore, they are sodium sulfate rhombic, sodium sulfate monoclinic, then solution of these two, and vapor. So these are the four phases which are present at point G. Then curve GH. Curve GH is the solubility curve of monoclinic anhydrous sodium sulfate. So, how the effect of solubility from G to H takes place with the increase in temperature, we can see the composition goes on decreasing. So, the solubility steadily decreases with rise in temperature, and the finally this curve ends at H. And here at H, the critical temperature at which this curve ends is 365 degrees centigrade. So at this temperature, solution and vapor phase, they merge into each other. So therefore solubility reduces to 0. Then curve H2I, there is no proper demarcation between GH and HI. And this is called as solubility of anhydrous sodium sulfate in water vapor. So as I have told you that two curves are continuous curves. Only differentiation point is this temperature 365 degree. So at 365 degree the point will be the H point. Otherwise there is no differentiation between these curves. So this table is for different quadruple points. What is the temperature at each point and what are the phases in equilibrium for each of the quadruple point. So at quadruple point B, temperature is minus 1.3 degrees centigrade, and phases in equilibrium are ice, sodium sulfate decahydrate, solution, and vapor. Solution and vapor. At quadruple point C, the temperature is minus 3.55 degrees centigrade, and phases in equilibrium, they are ice, sodium sulfate heptahydrate, solution, and vapor. The quadruple point D, temperature is 24.2, sodium sulfate heptahydrate and hydrous sodium sulfate rhombic, solution, and vapor, they are the four phases. At F, temperature is 32.4, heptahydrate, anhydrous rhombic, solution, and vapor are the four phases. At G, temperature is 254, anhydrous sodium sulfate rhombic, monoclinic, solution, and vapor. These are the four phases, and at all these points, the degree of freedom will be 0 and system will be invariant system. So this is the book which has been used for preparing this lecture, Chemistry for Engineers by Harish Chopra and Anupama Parmar. This book has been published by Alpha Science UK and as an international edition, and national edition of this book has been published by Narosa Delhi. Thank you very much.